Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about Z-test of proportions. This is another hypothesis testing, but this is different from whatever we have discussed already or the other test that I will be discussing. So it's different from T-test or the Z-test, the normal Z-test. Okay. How is it different? Because it has the word proportions. So let's understand that. And before I dive into that, let me set up the agenda. So we'll discuss what is sample proportion, where we'll understand what does proportion mean, and then we will see how binomial distribution comes into picture because of the proportion, and then we'll see that using CLT how we can approximate this to a normal distribution. We'll do a brief discussion and we'll do some derivations around that, and then we'll dive deep into the one sample Z-test of proportion and two sample Z-test of proportion, and then we'll see a small problem that will make everything clear. Okay, so let's start. So what do we mean by the word proportion here? So that is the key. Earlier, whatever we are dealing, say for example, if I'm doing the normal Z-test, so the data is normally distributed there. So we have, when we are dealing with numbers, so we will have some numbers here and the data will be normally distributed. We'll have this curve. So all these plots that we see in the PDF, all these are numbers, right? We have some numbers and corresponding to that we have some values. But what if instead of numbers we have categorical data? Categorical data. Okay, for example, success, failure. Okay, success and failure, yes, no, defective, non-defective, male, female, such kind of categorical data which cannot be represented directly in numbers. So that kind of data is called categorical. So how do we measure that, or how do we formalize that as a distribution? So we have discussed this. Whenever you hear of success and failure, what comes to our mind? Bernoulli trials. Okay, so Bernoulli. So tossing a coin, remember from that, right? So whatever is in the form of success and failure, that can be modeled as a Bernoulli distribution or Bernoulli trials. And when we do that, repeat that trial n number of times, where the trials are IID, independent and identically distributed. Independent means all the trials are independent, and ID means they are coming from identical distribution, that is Bernoulli. So what becomes? So Bernoulli is for success failure, and when we do it n times, it becomes a binomial distribution, and we have studied this in the past. If not, I'll put those links in the video description. Okay, just check that. So n Bernoulli trials, that will give me the binomial distribution. And now the proportion part. So let's come back to this is for categorical data, and how do we model that? So we understood this. So what does proportion mean? So here this is success. In terms of success, if we define, so proportion means, so here the proportion word, this means proportion, it comes from ratio and proportions. That's the fraction we have. So it's the fraction of success. If you have n trials, right, what is the fraction of success in that? So for example, if I do 10 heads and if I define my success as heads, and if I get 6 heads, so 6 out of 10 will be my fraction of success, or the proportion, that will be 0.6. Okay, so that will be equal to number of success, total number of success in n number of trials, total number of success, whatever we define as our success, divided by total number of observations or samples, total number of samples or observations, whatever. So this is what proportion means. Okay, and the Z-test generalizes to capture this categorical data, and it measures, it provides you a test to compare proportions, okay, where we have fractions of success and we have categorical data. And let's formally understand that. So what is Z-test of proportion? Z-test is again normal distribution, and we'll come to that how it comes to normal distribution. So we'll write Z-test of proportion. We'll do some derivations in the middle from the central limit theorem. Not exactly derivation, we will take whatever is coming from central limit theorem, and then we'll define our proportions and we'll get some derivations out of that. Okay, so whenever we are dealing with categorical data, or then only we talk about proportions, because it cannot be modeled as numbers because they are not numbers. Okay, So that is, so when we are dealing with categorical data, yes, no, success, failure, okay, that kind of success, failure, we have seen that, okay. So that is there. And then, and whatever is the observed proportion, so it can be, as I mentioned earlier in the agenda, right, we have one sample z-test or two sample z-test. So it's simple to one-sided t-test, z-test, like that. So when we have one-sided test, so we compare a sample proportion or observed sample proportion to a known or hypothesized proportion. Okay, so we compare this observed sample proportion to a hypothesized proportion. So that is one, because the other part here we have hypothesized already. We know this should be the value, and then we compare whether the samples justify that claim. So all this comes under, this is another kind of hypothesis test only. So that's what we are understanding. And if it is two-sided, means here we had only one sample, another was hypothesis that we know that this is the value. Okay, we claim that this is the value. In two sample test, there will be two independent sample proportions, two independent sample proportions. Okay, and there they will be compared. Okay, and the comparison will be made. They will be compared. Comparison between two independent sample proportions. Okay, I hope this is clear. This is the formal definition. And now let's understand how. So we model the success and failure as Bernoulli trials, and because there are n such trials, we model it as a binomial distribution. And from the prior, okay, for the from the distributions, we will derive how we will model our proportions. So in the sampling distribution, we'll model our proportions. So how does that come into picture? So we'll gradually move towards that, and we'll follow the maths along. So let's assume, say for example, whatever we are observing, the data is y is a Bernoulli. Okay, so that's the Bernoulli with probability of success as p. Okay, and then there is a random variable. These are random variables. Okay, and we are telling that these are the distributions. So this is random variable. This is, so these are discrete. Remember, right? These are discrete, countable. Okay, so these are random variables we are modeling. And if for n Bernoulli trials, we have binomial. Binomial, and the distribution is given with by n and p. N is the number of times we are doing the trial. So for Bernoulli n trials, what is the mean and variance we have seen in the past? So the mean here is equal to n into p, and the variance here is equal to n into p1 minus p. We know this already. Okay, and where p, what do we know about p? P is the, what is p? This is the true probability of success. So this is the where we are modeling true probability of success. True probability of success, and n is equal to number of trials or number of independent trials. So IID, this RBR IID, so that will always be there. Okay, and now let's define. So this is our trials. So now we are doing proportion. So what is the proportion of success? So this X will, this binomial trial will give me the PMF or the for the number of successes. It can be like 0, 1, 2 till n. So this will give me the PMF, complete distribution. So binomial distribution gives me the number of successes in n trials. Okay, so what will be my sample proportion now? So let me say, for example, if I say here itself, so my sample proportion, the proportion what I have. Okay, what is the proportion? This is given by a word p hat. This cap or hat, this cap is there. Okay, this p hat is there. This is equal to the number of successes that I get from the binomial trial by the total number of trials. That's what we have defined it. That is total number of successes. So that total number of successes will get from the binomial, and n is the number of trials, number of sample size. So that's how proportion is defined. So we are defining it now formally using our distributions, known distributions. So we can get the maths, and now everything we can analyze better using the maths that we know already. Statistical analysis we can do. So you have x as binomial and n is the number of distributions. So this is how we will do it. This is the proportion of success in our sample. Here, sample proportion. Okay, so this is the proportion of success. So we are modeling because P is the probability of success. So this is proportion of success. This is how we are modeling. So this is very important. Just remember this, because this is very important. This part, this will come again and again. So the proportion of success is total number of successes which is coming from the binomial divided by n, the total number of trials, or total number, or the number of samples or sample size, all are same. Okay, so that's how we have defined our sample question. Now let's proceed. So now this is what is the mean. We know the binomial mean. This is equal to the expected value. If this is x, right? If this is binomial, this is expected value of x, and this is equal to variance of x. If these are the expected values and variance of x, what will be the expected value of my sample proportion now? So my expected value of sample proportion is equal to expected value of x by n. So expected value of x we know, because this comes from binomial. So this is np by n. So this n gets cancelled. So expected value will be p. So this is your expected value or mean. This is equal to p. Same. This has become this. And then expected value or variance. What will be the variance of this? Because we want to know the distribution. Variance of this p hat. This will be variance of x by n. And by by variance formula, right? That variance of cx is equal to, if c is a constant, this is equal to c square times variance of x. This constant square times it multiplies outside. Simple. Because every time will be, every term in the distribution will be multiplied by c square with c, and then we take the square. Okay, so that's why this square term will come out. So this is because of that. You can do the math, it's very simple. So this will be, so here n is our constant. Similarly, n is the constant, 1, or say 1 by n. So this will come out. So this will become is equal to 1 by n square, variance of 1 by n square times variance of x. This is equal to 1 by n square. What is n square times? What is variance of x? This is your variance of x. np into 1 minus p. n times p, 1 minus p. This n and this square get cancelled. So this is equal to p into 1 minus p by n. So this is your variance of p hat, or this is equal to variance of x by n. Same. So now we have got the expected value of our sample proportion and the variance also. This is very important. So this is your variance. And now whenever we are dealing with, so now let's bring in our central limit theorem. So this is the binomial. The binomial is a discrete, it is for discrete, right? So if we have n such data, so we'll get PMF for this. So they will get bars for each value. What is the total number of success at each value? And if n is very, very high, okay, as n tends to infinity, of n is very large, you will see that these histograms, so this is like 0, or then 0, 1, 2, 3, like this till n. If you see, okay, so this, if you see, this will come out to be like a, if you see all the points, then n will go this side. Okay, this can be approximated as normal distribution. This binomial, okay, because all these PMFs will be histograms at each point. This will be PMF probability at each of the values. Probability of 0 success, 1 success, 2 success, 3 success, like that till n successes. So this will follow a normal curve. This is because of the central limit theorem. Okay, and we can approximate this binomial as normal for very large n. So we can write it formally as if X is a binomial with parameters n and p, so this can be approximated, okay, as n tends to infinity for very large n. Okay, this X can be approximated as a normal distribution with mean as np, whatever is its mean, and the variance as whatever is its variance. The variance was np into 1 minus p, right? So this is your mu, this is your sigma square, right? So this can be approximated as this for very large n, and this is because of CLT. CLT is central limit theorem. If people who don't know, watch that video. I have explained there also what is this, because of all this will converge. Similarly, if this can be approximated and my proportions are coming from this binomial, so similarly my binomial, the proportion can also be approximated like this. So my proportion, whatever this p hat, where is p hat, can be also approximated as a normal distribution with mean, what we have calculated the expected value with mean p, and variance we have calculated as p into 1 minus p by n. So this will be its mean and variance, because this is just by n we calculated from here. This is the expected value which it came as p here, and the variance came as variance of p hat. This is the expected value of p hat, and the same thing I have plugged in here. Just because my total number of the sample proportion is defined by as number of successes by total number of samples, and from that became that this is the normal distribution for very high n, and that's where the normal distribution comes in. And then from here, that z this is for standard, this for standardized z, right? N01, this z score is valid, a z test. For 0 means 0 mean and variance is 1. So this z score or this z test comes into play as soon as we are dealing with normal data, which because of central limit theorem, this binomial can be approximated as a normal distribution, and because my sample proportion is coming from the binomial distribution and we have seen that relation, so similarly my sample proportion can be approximated as a normal distribution with mean as p and variance as this term. Also from the central limit theorem we know that the term, there was standard error, you remember. So whatever parameter we are, which has approximated, which was became means after, because of central limit theorem, whichever parameter became normal. So what we did in for example in other one, the mean with the sample means, they became normal, right? So they formed a normal distribution. So the variance of that parameter is the variance, and the standard deviation of that parameter is called standard error. So so what is standard deviation? Standard deviation is equal to square root of variance, whatever. So whatever parameter which has been approximated as normal because of central limit theorem, so the standard deviation of that parameter can be inferred as standard error. That term is called standard error. So what will be our standard error here for approximations? So that will be square root of the variance of my standard proportion, and which has been computed as this p into 1 minus p. I'll make it more clear. P into 1 minus p by n. I hope this is clear. So the parameters will change, but this is just a parameter, inference parameter, this which is the standard deviation of the new parameter which has come into play because of the central limit theorem, which was mean there in the central limit theorem example, and here this is the, for proportions also, this is the success rate for the proportion. Okay, here this is the rate of success. or the proportion of success. I hope this is clear. This is the standard error. This is just the square root of the variance. Okay, now if this is clear, so there is one more condition for which this approximation holds. So the probability for this binomial itself, not for this, for the binomial itself, for the binomial to be approximated, we had the condition, right? For means the sample should be greater than n should be greater than or equal to 30. That is considered as large for practical purposes. Similarly, for binomial, the probability should be, net probability should be greater than or equal to 10. And also for the success, and for also the failure also, that is n into 1 minus p. Sorry, the total number of success should be greater than or equal to 10. Sometimes it's even 5. Sometimes this value is also equal to 5, but we take 10 and we do this. Okay, so this is what counts as that this is a good enough. The sample size is large, and beyond this, this can be approximated as normal. Below this, if the sample size, the number of sample size is less than 10, or this number of successes, this is not sample size, the number of success, total number of success is less than 10, or the failures also is less than 10, then we cannot approximate that distribution as normal. The binomial cannot be approximated as normal. So that's the condition. I hope that's clear. Let's move on. So if this is clear, now everything will fall. This is the maths I wanted to do. Everything, the rest of things is similar to other tests. So let's do the one sample Z test of proportion. So I'll do first one sample Z test of proportion. So this is your, so as I've said earlier, this is comparing. What does it compare? It compares the sample proportion. I have mentioned this earlier. Let me just check. Okay, I just mentioned it. Okay, I didn't write it. Okay, so let me write it again. I thought I have written it. So what it means is that it is the observed proportion comparing, when we are comparing two. So this is to one sample, right? So we are comparing observed proportion, compare observed proportion to a known hypothesized value. So one side is fixed, so other side is only come from a compare observed sample proportion to a known hypothesized value. So we have the sample from the sample, one sample we have, and the other side is fixed, that we know that this should be the value. And when we compare these two, this is one sample, and in the two sample, both are independent groups. Okay, both are independent samples. So this is there. Let's put the so next thing is the we have the test statistic. So what will be the test statistic for this? For n test, we have the test statistic, like we had for t test, z test. All the tests will have a test statistic. So it is called z. Okay, as because it's a z test, so it will be similar. So let me define all the terms. So what was our p hat? P hat we have defined. This is the proportion of success. That is equal to x by n. Okay. Then there is something called p naught. That is a specific proportion. Okay. Under null, this is specific proportion or the hypothesized value. Specific proportion under null hypothesis. Okay, consider null hypothesis is true. So that is a specific proportion or the hypothesized value. This is this against which we are going to compare. So p hat and p is defined, and now standard error we know. So this will be standard error. 0 is again the standard error under null hypothesis. H0 is null hypothesis. Okay, and the z statistic. So what will be? So my z is defined as, so this is your z observed or t observed. This is your t observed generally is equal to z observed. You can write this, and this is your difference of the proportions. So this will be p. Let it be 2 only. This is your specific, or this is a hypothesized value. Okay, and this will be divided by the standard error. So what is the standard error term? Generally that is used for standardizing. So here it was P into P naught into 1 minus P naught by N, right? So this term is the standard error. Other terms we have defined. N is the number of samples. Okay, standard error we have defined already. So this is your variance, square root of variance, and this is coming from the central limit theorem. Simple. This is your test statistic for one-sided z-test of one sample z-test of proportion. Okay. So this is simple. These are the two proportions. That's how we do. In case of means, we compare the two means, and there is a standard error below, or some form of standard deviation. So standard error is a standard deviation only, okay, but of the observed statistic, and we infer something from that. So this is a kind of standard deviation only, standard error. It's nothing different. So let's do next two sample test. Two sample z test of proportions. So this is again test if there is a significant difference between the proportions of two independent samples. Okay, this is to compare two independent sample proportions. So both the values are coming from two different samples. Earlier one side was sample from the sample, other was hypothesized. Okay, so that's the difference. That will be the running difference everywhere. And then generally this is the most, okay, this is why it is important. So just make a note. This is the standard test used in A/B testing. Okay, this is the standard test used in A/B testing whenever we have categorical data, right? This is a standard test used in A/B testing. Okay, we will do an example also that will make it amply clear. And how do we define it? There are more terms here. So there is one P bar, okay, which is your average of total success. That is total success. This is average across both the samples, okay, by total success in both the samples by total sample size. Total sample size, that is across both the samples. What is my total success? So that is total success will be x1 plus x2 if there are two samples by n1 plus n2, right? So it can also be written as, because my p hat is equal to x by n, this implies x can be written as n into p hat. Okay, so if I replace this x by n p hat, so this will be n1 p1 hat plus n2 p2 hat by n1 plus n2. So in case we have to define it in terms of this one, p1, we have this, if these proportions are known. Okay, same thing. And now what is my standard error? This p hat is for combining the two success proportions. Okay. Then we have the standard error. Standard error term in the denominator. So this is standard error for p1 and p2 for both the samples. This will be equal to square root of, and that's why this average p bar is used. Okay, so that is equal to p bar into 1 minus p bar, and then into 1 by n1 plus 1 by n2. So these are the sample sizes of two samples, and p1 p2 are the proportions of the two, and I take an average of, this is the way we take the standard error. So how do we take a average of this? This is the way we take the proportions of both the samples into account and make it into one standard error. Okay, and now simple, we have both the terms sorted. So my z-statistic will be z-statistic or test statistic when I talk in terms of hypothesis testing, or this can be equal to T observed, or this is equal to Z observed, whatever, when whatever you are observing under null hypothesis. So this will be equal to P1 hat minus P2 hat. So the difference between two proportions minus divided by the standard error. Standard error is given by P hat into 1 minus P hat by into 1 by n1 plus 1 by n2. We know all these terms. This is the proportion of success of first sample, proportion of success of second sample. Let me write it. Proportion of sample. Another terms are known. This is sample size. Okay. So these are just formula. Just put the numbers. Okay, and then you will get the values out. So just plug in the numbers. If you understand the concept, now plugging in the values will be very easy. So if this is clear, let's do a quick problem and understand this. Okay, I hope this is clear. The two sample test. It is just formula. This formula is coming from a derivation. So it's in the general format. Always we have some kind of difference in the top, in the numerator, and the denominator has some form of standard deviation. Let's move. So let's do a question. So we are doing a A/B testing to compare the two designs of a website. Okay, so we are doing a A/B testing to compare two designs of a website, and we have some data. So after from this design, how many users signed up, etc. So if I have that data, so I can from that I can do test of proportion and find out which is a better design. Okay, so I have A/B testing to compare the two designs of website and to see if, and my claim is that the design, there are two designs, A and B. Okay, so there are two designs, A design and B design. So for the name, and my claim is that B increases the conversion rate. This is my claim. So maybe A is the existing design and B is the advanced design. Maybe the color of some button is changed or the web page font is changed. Some minor change has been done, or major also. And then I say that the new change, which is measured by B, increases the conversion rate, and for that I'll have data, and from that data we'll do the Z-test of proportion to understand whether the claim is true or not. And this is a hypothesis testing. We make a claim, and then with the data in the sample we validate whether the claim is true or not. Okay, so let's move. B increases the conversion rate. Conversion rate, that is proportions of visitors who signed up. Conversion rate means proportions, again it's fraction, right? Proportions of visitors who finally sign up after visiting your page. Okay, so that's the test. So let me write. So you have group, okay, and then we have number of visitors. Okay, so this is your N, and then there are number of signups. So this is your success, this is X. So this is total number, and out of that how many signed up, that is your success, total success coming from binomial. And then this is your conversion rate or the proportion conversion rate. This is your P bar is equal to X by N. So let's write. There is group A, group B. Say for example here 1000 visitors here, and in the group B you have 1200 visitors. Here 80 people signed up, here 114. I'll do the maths, okay, and I'll leave up to you to verify that quickly. And what will be my conversion rate here? So if this is A, PA will be 80 by 1000. So this is clearly 0.08. This is simple. And then PA for B would be, the proportion for B would be 114 by 1200, and I have computed this already. This comes out to be 0.095. Okay, and the numbers you can just put it and validate. I'll just keep on writing. The main idea is to understand how do we do hypothesis testing for the categorical data, which is coming from Z-test of proportions. We have understood the theory, and let's put the numbers. So how do we do hypothesis testing? Let's follow the thing. The very first thing that we do is, let's solve it, that we fix our null and alternate hypothesis. So what is our null hypothesis? That proportions of both are same. There's no difference in conversion rate. So I say that the proportion of conversion is no difference. There is no change. That's what is null hypothesis. No change. That implies proportion A is equal to proportion B. There's no change. No change in conversion rate. That's what null hypothesis means. There's nothing has changed. There's no difference. Status quo is maintained. And what is alternate hypothesis? So that's the claim that I'm making. Depending upon that, the kind of test, whether I'm doing a right tail test or left tail test, one-sided test or two-sided test, that will be determined. So here I say that B increases the conversion rate. So my B design is better. Okay, that's what I want to say. Okay, there are two designs, and design B increases the conversion rate. So I say that proportion B is greater than proportion A. Okay, that is B is better designed in terms of conversion rate. Okay, B is better designed. So whenever we are comparing greater, something is greater than, so this will be a right tail test, and again this will be only one tail test, because if it is not equal to, then we are comparing on both the sides, less than or greater than. But we have only one side, less than or greater than. If it is greater than, I move to the right tail test. If it is less than, I move to the left tail test. Okay, as simple as that. So let's move. This will be a one tailed. Okay, that will be right tailed test. And let's put the formula. And also let's check the large number condition, sample condition, whether I have enough samples or not. So the large sample condition, so that it can be approximated. The binomial can be approximated as normal, because from there only all the formula has come. So large sample condition. What was the last sample condition? That number of successes should be greater than or equal to 10. What is our number of success here? NP, that is your X, total number of success. Here it is, it should be, no, not 1000. It should be greater than or equal to 10. Here clearly this is 80. Okay, and the number of failures should also be greater than 10. So clearly if success is 80 and we have 1000, so this is greater than 10. So no problem with this. So always make, I'm just pointing it out, because do this test if you have small sample size. Okay, you count the number of success. We have 80 here, so it is clearly greater than 10, and the failure is the remaining 920, so it is clearly greater than 10. I hope that makes sense. And then we consider with the continue with our test statistics. So we have this null hypothesis and alternate hypothesis is fixed, and then what kind of test we are going to do? So we are going to do we have finalized here itself after doing this, that this is a one-tailed right tail test for, and this is a Z test. Okay, this is a two sample test of proportions, because I am comparing proportions. So this is my test, and then for that, what will be my test statistic? So my test statistic is, it will give me the distribution. The underlying distribution is normal, but the test statistic which we will measure is what is the formula here? This is the formula. Let me copy this. I'll put the values. And where P bar was equal to, what was P bar equal to? This square root of, I'll just copy this. No, not this one. What is this is the P bar, right? This is the P bar. Okay, sorry, this is the P bar. Because I have written it already. So P bar is equal to this. Because I need to use P bar in the formula. So all these values are already present. I have x1, x2, that is xa, xb. This x, this is there. And n1 and n2 are there. This is n1 and n2, na, nb. So I can directly compute P bar. So my P bar will be equal to NA is 80, NB is 95, no 114, sorry, 114, and the denominators are 1000 in one sample and 1200 in one sample. I have calculated this already. This should come out to be 0.088. Okay, this is a P bar, and then rest of the numbers. So let's calculate the standard error. Let's calculate the denominator separately. This is my standard error. Okay, so this is my standard error is equal to this. Okay, the square root is on complete thing. So this is equal to p bar is 0.088 into 1 minus 0.088. This will be, whole thing will be under square root, and this will be 1 by n1 is 1000 plus 1 by 1200. If you compute this, this should come out to be approximately equal to 0.0123. This is just calculator, okay? And then finally my z observed or equal to t observed. If I talk about test statistic, generally it is z observed, okay? Whatever the test statistic I'm measuring, so this should be equal to because I'm measuring whether PB is greater than PA or not by standard error. So my PB is what is my PB? We calculated earlier. 0.095 and 0.08. So 0.095 minus 0.08 and the standard is 0.0123. Okay, and this will approximately come out to be 1.22. So this is your final Z observed. What to do next? So this we have to compare against the Z score. So this we have got your test statistic value we have got. Now we have to find the alpha. So what is your alpha? Alpha is say 5%. Okay, so this is your 5%. This means that this is your 0.00. This is your significance level beyond which, okay, if your null hypothesis will be accepted or rejected, this is determined by your alpha. So, and this is a right tail test. So we have found out that is a normal distribution. Here your mu is there, and now we have found out that your z observed is equal to 1.22, and for, so this is my p value. There will be some area under this corresponding to this. Okay, so this will be my p value, that is equal to area under curve for this probability of observing t greater than equal to t observed or d observed. P value is probability of observing t value greater than equal to t observed. This is the t observed, z observed. Okay, this is the area under the curve. Now, if for this significance value level, okay, this significance value level or whatever significance value, I think for this significance value, if it is coming here, okay, my t alpha is coming here, so this is so my z observed is greater than this, so this is greater than 5%, so I will accept my null hypothesis. But if my t alpha or the critical value comes here, means the area under p value is less than 5%, so I will reject my null hypothesis. So how do we find out? So what will be the z score for alpha is equal to 0.5. So my z score, because this is normal distributed, for alpha is equal to 0.05, 5% significance value. So this will be equal to how much? So let's see online. Where is it? So this is a chart. You can just search for Z score table PDF, and then you can scroll through this. And here if you see hypothesis testing critical values is here, and here if you see 0.05 is the significance level. And for left-tailed or right-tailed test, left-tailed is minus 1.645, and for the right-tailed, we have right-tailed test here because it is greater. It is 1.645. So this is equal to 1.645. So this is definitely, okay, this is definitely greater than 1.22. Okay, just a minute. So I will just make it here, and this is your t alpha. This is equal to 1.645. This is more right. This means that the area, so this value will be, okay, let me color it for you. So this value is your significance level or significance value. Okay, this is 5%. So definitely my area under the curve, the p value, this shows that my p value is greater than significance level, which is 0.05. or 5%. The area under the curve on this side will definitely be, because there is some more area under the curve under this. So this is greater than this. Means we fail to reject the null hypothesis. So what is the conclusion here? We fail to reject null hypothesis. So what is the conclusion? That whatever changes we are observing, that in the conversion rate, that is that we have observed, that is due to some random chance. It's not because the design B is better, because we have calculated here that for this significance level, the area under the curve is less than the significance level. So we fail to reject the null hypothesis. This means that, what was the null hypothesis? There is no change in conversion rate, and whatever we are observing, okay, that is not statistically important, significant, and that is just random or by chance. So whatever improvement in the conversion rate we have seen, that is because of some random chance. I hope now this is clear. We have rejected the, we fail to reject means we accept, okay, we accept null hypothesis. We fail to reject, or other words we can say, but generally we say we fail to reject. I hope this is clear. So the conversion rate, whatever you have seen, we have seen clear improvement here, right? This is from 0.0 to 0.9, but after the test of proportions, we found out that this is below the significance level. So this is by random, by chance, and is not because design B is better. I hope Z test of proportions is clear. In this video, let's do a quick recap of what we have done, summary. So we understood what is sample proportion. Sample proportion is fraction of success, that is total number of success divided by number of samples. And when is Z test of proportions required? When we have categorical data. Generally T test or Z test, we have numerical data 1, 2, 3, 4, where we can compare. But what if we have success, failure, yes, no, male, female, defect, no defect kind of things. So there, this is a categorical data, and there Z test of proportions is required. And this data we model as Bernoulli trial for one, and then this is modeled as binomial distribution. And for very large number, for very large n, this can be approximated as normal distribution. We saw that, and from there we calculated the expected value of my proportion, and from there we got the standard error value, and the same thing we put into the formula everywhere. And then we saw one sample Z test proportion where we compare the observed sample proportion to a known hypothesized value, and then we found the test statistic. This was the formula, that this is the difference between the sample proportion and the hypothesized value divided by the your standard error, which we have calculated earlier. And then two sample test compares two independent samples coming from two independent groups, where, and this is the standard test for used for A/B testing in websites, okay. And then we saw there is a p bar, average success, in the formula, and we put it in the formula, and the standard bar, standard error formula include the p bar. We had this formula, and then we have a Z test statistic formula. This we used, and we solved a problem for hypothesis testing. And this whole tool is one of the many ways to do hypothesis testing. This is one of the many tests to do hypothesis testing. This is your Z test of proportions. I hope you understood whatever has been covered in this video. Thanks for watching this video. Have a great day ahead, and bye for now.